All right, so back to particle detectors. So I was talking about a Geiger counter, which is like a handheld wand, like what you would see at an airport, except there it's looking for metal. But in a Geiger counter, it's looking for radiation. Another example are called ionization chambers, where the radioactivity would cause you would see its path. The same with the cloud chamber. There was actually a student a few years ago that made a cloud chamber as a science fair project, and they used liquid nitrogen to form like a cloud, a water vapor cloud almost, and they used the insides of a smoke detector to get the radiation being given off. It was kind of cool. Another one would be a bubble chamber. Spark chamber. And a scintillation counter. Scintillation. So again, for these, I would just like you to recognize their names as particle detectors. The one that you will hear most often in your lifetime would be a Geiger counter. Okay? So particle accelerators and particle detectors, with them we are now ready to move into the world that is known as artificial transmutation. So the alpha, beta, and gamma decay we were talking about were radioactivity that happened without us doing anything. There are particles that are radioactive. But the artificial transmutations are ones that we are causing. They are ones that we shoot a particle that we sped up in these particle accelerators, and we shoot them at a sample, and the sample absorbs this high energy subatomic particle. The sample absorbs it, the atom absorbs it, the nucleus absorbs it, it becomes unstable, and then it spits out something. Okay, so it's called artificial because it wouldn't happen on its own. Most often we would be shooting protons, alpha particles, electrons, maybe neutrons, maybe gamma radiations, gamma rays, maybe even high energy deuterons, the isotope of hydrogen. Okay, with the hope that again the material that we're looking at would absorb it, and then emit things that we haven't discovered before. And sure enough, it works. So one example would be if you shoot if your sample is nitrogen 14 and you shoot high energy alpha particles at it. Okay, what happens is it absorbs and breaks down. Now you'll always be able to recognize the artificial transmutation because on the reactant side there'll be something added in. Whereas when it was just spontaneous transmutation, there was just one lone reactant. Okay, so whenever there's something added in, it means it's us doing it. Okay, and so when you shoot alpha particles at nitrogen 14, what you end up getting out is oxygen 17 and a proton being given off. So I'm writing it as a 1,1H because it's a proton that's being emitted. Now lots of times though, when we do something like this, the new thing that we've created, the isotope that's produced, is often radioactive and will break down. So for example, if you take aluminum 27, and aluminum's 13, and you shoot alpha particles at it, you will end up getting phosphorus 15. And what's given off is a neutron. Okay? But phosphorus 15 isn't stable. So if you wait a bit, phosphorus 15 will actually break down into silicon 30. Phosphorus 30, excuse me, will break down into silicon 30. So if you look here, what must be given off? Well, it must be a 0 on the top, and it must be a positive 1 on the bottom. But wait, we don't have anything that's 0, positive 1. And so we called this a positron. Positron. We now know it's actually a positive electron. Okay, a positive electron or a positive beta particle. And lo and behold, a regular neutrino is given off. So a positron, this is called positron emission, or positive beta decay, because we now know it's the antiparticle of an electron. Okay, so positron emission or positive beta decay. So you could write the positron as a 0, positive 1 e, or you could write it as a 0, positive 1 beta. They are the antiparticle of the electron. But back when we first found it, we didn't know that electrons had antiparticles, so we just called it a positron. But we now can also call it a positive beta decay. Okay? Now, what's actually happening is, and this happens when there's a nucleus that has too many protons for the number of neutrons. Remember, beta decay happens when there's too many neutrons for the number of protons. But this time it's too many protons for the number of neutrons. So what's happening happening inside the nucleus again is a proton is splitting up into a neutron and a positron. And a neutrino is given off. So when it's an electron, it's an antineutrino, and when it's the anti-electron, it's the regular neutrino. Okay, because a beta particle or a positive beta particle or a positron is really an anti-electron. So this is what's happening inside the nucleus. The neutron stays in there, but the electron and the neutrino are ejected. Because the neutron stays in there, the atomic number goes down by 1, but the mass number doesn't change, right? So the proton becomes a neutron. Okay? So you see a decrease in the atomic number, but the mass number will stay the same. Now, it could also happen that you would have regular beta decay as a result of artificial transmutation. So you could get a beta particle being given off in some samples after it absorbs whatever you're firing in. You could get alpha decay. So those ones didn't excite physicists as much as ones like this that we wouldn't have found naturally. Okay? So over the weekend you will have some artificial transmutation equations to balance out. All right?